Hey dudes, Dude the Builder here, and in this episode of Zig and Death, we're going to be talking about the multi-array list. We already saw the normal array list that we can find in the standard library, which provides growable array-like data structure. In Zig, as in other languages, arrays are of a fixed size that has to be known at compile time. The size is actually part of the type. But in the case of the multi-array list and the array list, we have data structures that pretty much arrange their data in an array-like fashion, but they can grow at runtime by making use of an allocator. The big difference when it comes to the multi-array list, when you compare it with the array list, is that the multi-array list allows us to implement what's known as a data-oriented development technique, which is called Structure of Arrays. When we have a normal array or an array list, and we have a struct like this one that we have here, this struct basically is the same struct that we used when we were talking about memory layout. We have three fields. First field is a U16, we have a U64, and then a U16, which basically means this is 2 bytes, this is 8 bytes, and this is 2 bytes, okay? Which also means that this whole data structure is going to be aligned in memory based on the largest field, which is the U64. So it'll have an alignment of 8 bytes, okay? That means that you can only have, when you have a sequence of these structs, like in an array, you can only have a new struct being placed at every 8-byte boundary, okay? That's basically what alignment means. And because of this, you have the situation that we saw in the memory layout episode, where you may need padding. Okay, this structure, we have here 2 bytes, that's 4, and 8 bytes, it would take up 12 bytes. But 12 bytes isn't a multiple of 8, which is the alignment. So we would need some 4 bytes of padding to reach 16 bytes, which would be the next multiple of 8. And that's what I mentioned here in this comment. This struct would take up 16 bytes, including the padding, if we were to put it in an array of many of these structs. And the difference here is that in a multi-array list, given the way it works, it would only take up the 12 bytes that it really needs. There is no need for padding. And we're going to see how that works in just a moment. To help us understand this concept, let's take a look at some images that I prepared. So here we have basically what a normal array would do with our struct. As you can see, this is similar to the image that we saw in the memory layout episode, where the struct is going to take up these 16 bytes, okay, of memory. And we have that since it's a normal Zig struct, Zig can reorder the fields to make the most efficient use of the memory. If you recall, if we were using the CABI type of struct, the extern struct, it would take up 24 bytes instead of these 16, because you can't reorder the fields in that case, and you would be using more padding. But since it's a Zig struct, it can reorder the fields, and that's what it's going to do. It's going to basically put the largest one here, B, is first, which takes up these first 8 bytes. Then we have A, which takes up 2 bytes, B, another 2 bytes, and then the final 4 bytes of padding. So that permits that in an array where you have a sequence of these foo structs, the next one is going to start at the next 8-byte boundary, okay? That's the one we have here, okay? And this one takes up another 16 bytes, and then we start another one, and that would be basically the sequence in this array-like structure. Now, in a multi-array list, let's take a look at the next image. We have a very different situation. Here, you're going to see that each field of our struct is going to be placed in a sequence by itself in its own array, okay? So a multi-array list, basically, if our struct has 3 fields, it's going to have 3 arrays. That's why this technique is called a struct of arrays, because it's going to be a data structure that's going to have 1 array for each field. And here in this case, we have 3 fields. It'll be 3 arrays. And as you can see, because each array only has fields of the same size, then we don't need any padding, okay? Here we have the B field, which takes up 8 bytes. And all consecutive B fields of all of the structs that we add to this multi-array list would be added to this array. And we don't need any padding in between to satisfy the alignment. The same thing happens here with the A field. It takes only 2 bytes, and we don't need any padding. And so we can have a lot of A fields here in this separate array. And the C field is basically the same identical situation as the A field with its own array. So as you can see, in these 24, we have here basically 16, 32 and 48 bytes. Here we have 8 C fields and 8 A fields and 2 B fields, versus over here we had 3 B fields, but we only had 3 A fields and 3 C fields, okay, in that same 48 bytes of memory. So the multi-array list is making a much more efficient use of that memory, because it doesn't need any padding to satisfy alignment by putting each field in its own array. And this technique, if you're dealing with small amounts of memory, small amounts of instances of a struct, it's really not recommended. You won't see any big difference. But when you're dealing with hundreds and thousands of these types of objects in memory, then is when you really can see big difference in memory, lower memory use, and even better performance, because this type of array like arrangement is what's known as a cache-friendly structure. Referring to the cache lines of the CPU. Since everything is in its own array and all these fields are tightly packed right next to each other, you have a higher probability that when you're going to access the next field of the next struct, it's going to be already in a cache line of the CPU, and that is much faster than having to read it from main memory, okay? So the multi-array list can offer that kind of advantage. And this is a data structure that has been really popular in the game development area of programming, because video games are a prime example of a scenario where you're going to have thousands and thousands of objects. And using this type of arrangement will be beneficial in terms of performance because of the cache friendliness, and in terms of lower memory usage. Okay, so let's go back to the terminal and let's see how we can use a multi-array list in Zig. Zig basically tries to make it as transparent as possible, really similar to how you deal with a normal array list. Obviously, there are going to be differences because it's a totally different structure that this data structure is using behind the scenes. But as you will see, it isn't that difficult. Here, we're setting up our allocator, as you already have probably been accustomed to from the other episodes. And here is where we instantiate our multi-array list. We pass in the type of the items, in this case, our food struct. And once again, this is a generic function that will return the type, and these empty curly braces here are the actual instantiation of an instance of that type. Here we use defer to call the deinit method. We pass in our allocator. you're going to see that one difference from the array list is that in many instances you have to pass in the allocator to the multi-array list methods. Here we have an example of doing an append. As you can see, we pass in the allocator here, and then the actual item that we want to append to our multi-array list. We're using here the tuple literal syntax here. And here, if an allocation is necessary, then it will be done with this allocator that we're passing in. So that's why we need an allocator when we use append. You can also pre-allocate the required memory for the number of items that you want to add. Here, we're using ensure unused capacity. For that, we pass in the allocator and we tell it that we want to ensure that we can add 2 more items to this multi-array list. And here then, once we do that, we can add those items by using append assume capacity. And as you can see, we don't have to pass in the allocator. And also, we don't have to use try here because we already know that we have enough capacity, having made this call to ensure unused capacity. Okay, that's another option that you have. Here we're going to see if you need like a one-off method of getting a specific field from the multi-array list. Then you have this items method, and you pass in this enum literal style name here. It will be basically the name of the field in the struct that you want, preceded by the dot. Okay, and what this will do, it will return a slice of the array of those fields within the multi-array list. Okay, so for example, here we ask for the A field. We would be obtaining here a slice of all of the A fields for all of the items that we've added to the array list. Okay, here we do the same thing for the B field, and here we do the same thing for the C field. Okay, so let's take a look at that output. Scroll here to the top. Okay. And here, first off, we have precisely for the A field, we obtain this slice here that has the values 1, 2, 3, and the same thing for the B field, and the same thing for the C field. Okay, so basically, that items method call will return a slice with the values for that specific field for all the items that we've added to the multi-array list. And then you can use normal slice operations on that slice, access any specific index, or iterate over the slice with a for loop. If you're going to be accessing fields very frequently, then performance benefit can be gained by calling this slice method of the multi-array list. What this will do is that it will basically pre-compute those slices for the fields. And the result will be here assigned to this sliced constant that we have here. And then we can call on that sliced constant, we can call the items method with our specific field. We're going to be here storing the return slice for the A fields in A fields, the same thing for B fields, and the same thing for C fields. And then once again, we're going to be printing out, in this case, we're going to be printing out the first element of the A field slice. So it would be the field A of the first item that we added to the multi-array list. Here it would be the field B of the second item, and here it would be field C of the third item. Okay, and if we look here in the output, item here where it says first has value 1, field B for the second has value 2, and field C for the third has value 3. Okay, and next up, we'll be using a normal for loop here to print out the elements of those slices. Okay, and that's what we see here in the output right here. This would be for the elements. We have the A field for the 3 items that we added to the multi-array list, and then we had the 3 B fields and the 3 C fields. Okay. You can also get an item, the whole structure, by using the get method and an index within this multi-array list. So here get 0 would try to get the first item that we added, and here we print it out, and we can overwrite an existing item with the set method. Here we give it an index and we give it the data that we want to insert, basically overwriting whatever is in that index. Okay, since the result of our previous calls to items are slices, and slices, as you might recall in Zig, are just pointers, then those slices are going to reflect the changes to the data. Okay, so having made this change here with the set method, we should be able to see that when we print out the elements of our slice, of those slices that we obtained previously. So let's take a look at that. This output right here, the A field, as you can see, in the case of the second item, which is the one with index 1, that's the one we use the set method on, we have a 4 here. Okay, the same thing with the B field and the same thing with the C field. Okay, so those changes to the data itself are reflected in those slices that we previously obtained with the items method, and also via the slice method. Okay, here we're going to see an example of like the array list, you can use the multi-array list as a stack because it has a pop method. The pop method will remove the last item of the multi-array list and return it here. We're assigning it to head. We're going to print it out. Here we're using, once again, the append method, which would be the equivalent of push in a stack, okay, because it adds it to the end of the multi-array list. And here we demonstrate how we can iterate using the while loop in its optional modality, because pop or null, instead of producing an error like pop would, if you call pop and the list is empty, it'll be an error. But if you call pop or null and the list is empty, you just get back a null. So here you can use that in a while loop, so you can iterate through the list, removing the elements until you reach the end, and then we print out. Okay, so that's basically here we had the first pop, which we assigned to head, and then here we have the result of iterating through the remaining items in the list. Okay, and finally, a word of caution here: you have to be really careful when you do modify the structure of your multi-array list, because if you have saved pointers or the slices that we had previously saved to variables, the A fields, B fields, and C fields, those are pointers themselves. Okay, so if the actual structure of the list, and when I say the structure, I mean if you add or remove elements, okay, you can do that with append or the different append methods. There are also remove methods, just like the array list, ordered remove and swap remove, or the pop methods that we just saw. Anything that changes how many items are in the array list, then that would basically invalidate those slices and any pointers to the items, because the structure of the list has changed. And this could cause new allocations and copying of memory moving around. So basically you have to have that in mind. If you have saved pointers or slices and you change the structure of the multi-array list, then those slices and pointers will be invalidated. So here what we're going to do is we print out the length of each of those slices that we obtained earlier, and then we print out the length of the list itself. And if you see here in the output, we have that those 3 slices still have a length of 3, okay, but the list itself has a length of 0. Okay, so basically those slices are no longer valid. Okay, it's really important to have that in mind. And with that, that's basically the functionality I wanted to demonstrate for the multi-array list. As you can see, it has much of the same functionality that you find in the normal array list. There are some differences that are necessary because of the way the multi-array list works internally. But basically, this data structure will allow you, in the case of having many structures in memory, that could otherwise take up a lot more space because of alignment and padding issues. The multi-array list will allow you to store that more efficiently. And aside from that, you could even have performance gains because it's a more cache-friendly data structure when you're dealing in certain scenarios where you're going to be accessing the same fields of different structs. Okay? So I hope you find this useful. Do the builder here. I'll see you in the next one.